demo I'm calling magnetic force and torque. So the first thing we're going to see is the magnetic force on a current carrying wire. I also have a similar demo to this that I do the magnetic levitation. So I do that test. But right now I'm going to be concentrating on the magnetic force on the current carrying wire. The deflection is going to be right to left. So I have the power supply. This wire is connected to the positive of the power supply. It's connected to this side right here, the one that's closer to you. And then the other one is connected to the other wire. So from your point of view, it looks like this. Like this. So the positive current is coming like this and moving this way and then going this way. So if I tilt it like this, the current will be coming down and then going into this way, farther away from the video, right? And then up the other side. So once I turn on the power supply, so the current is coming down and then into the board. So I'll say the current is going into the board, right? The way that I have it set up. And then the magnetic field of the magnet, the north is up on the top. So the north is up on the top and the south is on the bottom. So the magnetic field is this way. So when I turn on the power supply, what is the expected deflection of the current carrying wire? So the force on the current carrying wire is equal to the current times the length times the cross product of the length and the B, right? So the length of the wire is, the direction of the length of the wire is given by the direction of the current. Since the current is going into the board, we take the cross product, so the current is going into the board and the magnetic field is facing down. So I crossed into B to the left. So the cross product of I and B to the left. So when I turn on the power supply, I'm expecting this to go up towards this direction. Okay, so what you can see is kind of oscillating. What happens is the magnetic force causes this to go this way, right? The wire goes this way, like that. But then the weight of the wire causes it to go back down. So it wants, its preferred position is down this way, right? So then it goes up, down, up, down, up, down, oscillates until it finally finds an equilibrium between the force of the magnetic field and the weight, right? So this almost can be a good problem. You can say, okay, what's the equilibrium angle? So you have the force of the magnetic field is the current LB.
You see that? So of course we could make a problem out of anything. Did you guys notice that it deflected to the left? No, you didn't? Maybe zoom in some more.
Till it finally finds an equilibrium between. So then it goes up, down, oscillates.
Let's see here.
Like that. But then the weight.
Oh yeah, you could tell right
like
here.
That.
You see how it's, you see how it's down on the left here?
Down. So it's preferred to.
Okay, so how would we do that problem? It's kind of like the pivot ball problem in electricity, right? So you have a wire like this. The current is coming down and then going into the board, and then the magnetic field is going like this, down this way, right? So what would be the direction of the magnetic force? So the current is coming this way. No, current is coming, going in, yeah. So then you just go 4 fingers in the direction of the current, curl it, and this is the magnetic force, right? FB. And then you have here the tension in the string, and you have here mg. Okay, and then you have here, this is theta, this is theta. So then you have here T sine theta. That's this component of the tension. That's equal to FB. And then T cosine theta. That's equal to mg. All right, remember the pit pole problem when we started electricity? It reminds me of that one a lot. So then we divide this. Then we have here tangent theta is FB over MG. And then FB is equal to ILB. And the angle between the B and the angle between the B and the I is 90 degrees. So we don't need any angle there. Okay, so ILB over MG. Yeah, so then depending on which one of these is given to you, if the I is given or the L, let's see what I did with that one here.
Position is that it finally finds an equilibrium between the force of the B, right? Then you have the weight of the wire. I'm assuming here the weight of the wire is at the center, is at the bottom, but reading technically it should be somewhere in the middle, right? The concentrated in the middle of the rod. But let's just simplify it. Say the weight is down here, and then there's a tension T, right? So we can make this into a good physics problem. We can say let this angle be theta. That means this angle is theta, right? So if that angle is theta, that angle is theta. So T sine of theta, which is the horizontal component of T. So it looks like this. This is T sine theta. That's equal to the ILB, the force of the magnetic field. And then T cosine of theta is equal to mg, right? The weight of the wire. So then you divide these two, right? And then the tension cancels. Tangent of theta equals the current times the length times the B over the mg, right? So right now the angle looks like it's about 5 degrees or so. It's tilted about 5 degrees. And then I don't know what the current is, but I can measure the current. I can put an ammeter in the circuit. And then the length would be the length from here to here. Okay? This way. It looks like it's about a length of about 5 centimeters. 0.05 meters. I can measure the current in the wire by putting an ammeter into the circuit. Right? I haven't done that right now, but you could do a good experiment here. You can measure the current in the wire. You can measure the mass of the wire, so you would know that, and then you would have 9.8. And then you can measure the angle, and then you can use this as an experimental way for calculating the magnetic field of that magnet, right? So now what's going to happen if I bring the magnets closer together? If I bring the magnets, I can adjust the distance between these magnets. If I bring the magnets closer together, what should happen to the angle? Right? The tangent of the angle increases, that means the angle itself also increases. So it should deflect even more, right? So I'm gonna bring the magnets closer, closer, closer. And you can tell here that I've made the magnets really close together now. And you see the deflection is bigger angle now, maybe 10 degrees or so, you see? So the magnetic force is larger. What should happen if I increase the current? Right now I've got the power supply set to 2 volts. If I increase the current voltage too much, there might be too much current going into it, and the fuse that you see where it says reset, and the fuse might pop out. So I want to be careful not to have too much voltage in there. So what I'm going to do is increase the voltage a little bit. Okay, now I'm going to put 3 volts. So you can see now the fuse popped actually. That was too much current. Right here is 1 volt. Right here is 1 volt right here. And 2 volts is the maximum that it can take. Let's increase to 2 volts. And you might be able to tell a slight difference in the angle, right? It's a larger angle. But if I go to 3 volts, the angle gets bigger, but the fuse pops. There's too much current in there. Okay, now I went back to 1 volt. One of the things I can try now is switch the way that the current is flowing, right? So I disconnect this, connect it this way. Now, which way is the deflection going to be? The deflection should be the other direction, right? So you can see it. It's basically the other direction. So now the current is flowing out of the board, right? The magnetic field is down. So when you do the cross product out of the board, curl your fingers towards the direction of B, and then the force is this way.
This is a great experiment to really practice the right hand rule, guys. You know, get your right hand rule down. That's a huge part of this next section. And a lot of people miss the questions because of that. Miss the problems on the test or something. They get the wrong directions.
Right, so now the deflection is this way. So I can zoom in on it so you can see. So you can see the deflection is to the right now. The other thing I can do is switch the magnetic field of the magnet itself. Right, so now what if I switch this way? And I go literally turn this upside down. And then hold it like that. So I haven't changed the wiring, right? All I did is just switch the north-south poles. Turn it on. Okay, now the deflection is to the left. You see? So the current is coming out of the board. The magnetic field is up now. Current is coming this way, and the magnetic field is up. So I'll show you the right-hand rule now for this. So the current is out of the board. Then I go up, then the force is to the left, right? So you go like this, but since the magnetic field is up, you can't go like this and curl it this way, right? So you've got to go like this, curl it this way, and the force will be to the left. So you can see that that happened when I connected them, right? So now I'm going to show you magnetic torque. So it's a little bit different to set up for that.
Take over our cities.
Okay, so in this problem, I guess we could experimentally calculate the theta. So let's say it was 5 degrees. And then let's say the current was 1.2 amps. Let's say the length was the same thing as, actually the length in there was about 10 centimeters, right? I think I said 5 or 10 centimeters. So let's say it was 5 centimeters. And then let's say it weighed, it's probably very light. Let's say 40 grams. So 1, 2, 3, so 0.04 times 9.8. Okay, so from there we can calculate what the magnetic field of that magnet was. Let's see if we get a realistic result. 5 tangent times 0.04 times 9.8 divided by 1.2 divided by 0.05. That's probably too strong. 0.57 Teslas. Yeah, that's probably too strong. Let's see, maybe the current is smaller. Yeah, maybe the current is smaller. The mass seems all right, and then this is 5 centimeters. Yeah, because I don't think the magnetic field of that magnet is that big, half a Tesla. Okay, you can kind of see there how we would do that. Okay, now let's do the magnetic force on like a rod.